Okay, picking up where we left off. We were talking about Copernicus and how he put the sun in the center, had the earth go around the sun and also rotate. Um, Tremendous simplification of explaining retrograde, but at a big cost. The cost included believing the earth moved. It sure doesn't feel like it does. Displacing humanity from the center of everything, which kind of hurts our collective feelings. Uh, Having a hard time accounting for the lack of observed stellar parallax. The stars didn't seem to shift back and forth, and they should. And he has to resort to saying that the universe is absolutely colossal, which again is scary and big. And so a lot of people, most people, large majority, would not accept what he said at the time. His book got out, about 600 copies got printed. Eventually, they kind of recalled it. Catholic Church finally didn't like it and tried to take it back. Copies were still floating around, so his ideas were known, though not terribly popular. I'm now going to switch to another person, a Great Dane, a great Danish astronomer with this name. Maybe you're supposed to say Tycho. I'm going to say Tycho because that's what it looks like to me, Brahe. But some people we know him by the first name, some people we know him by their last name. We're just going to call him Tycho. Everybody else does, it seems. He's a weird guy. He was born in Denmark in maybe 1546 or somewhere in there. So he's born a little after Copernicus dies. Maybe the first thing to tell about is how his family expected him to be a lawyer because the family had a sort of a noble background or something, but nobility wasn't really that big a thing anymore at the time. And they wanted their kids to bring the family a good name. He was expected to be a lawyer, but no, guess what? He had a secret dream to be an astronomer. He had to be kind of sneaky about it. But I think he had some uncle who slipped him an astronomy book or something. So he was into that. Now, when he was 20 years old, he was doing some astronomy stuff, casting horoscopes because astronomy and astrology were still kind of mixed up. And it seems he predicted that the Sultan of Turkey was going to die. Turned out the Sultan of Turkey had died 6 months earlier, and so all of Tycho's friends started making fun of him for making this retrodiction, and they kept bugging him at a series of Christmas parties. I know this is a strange story. Finally, this one guy named Manderup Parsberg, you don't need to know that, takes it too far. Tycho gets mad, says, let's take this outside. So they go outside. Swords. They had a sword fight. And in the sword fight, Manderup Parsberg chopped off Tycho Brahe's nose. His nose fell in the garden. He went home without a nose, bleeding all over the place. Spent 3 months in self-quarantine and made him a set of noses and some kind of paste to stick them on with. So for the rest of his life, he wore prosthetic noses of his own making, supposedly made of gold. I think it was really just like gold plated or something. Anyway, so this is a guy with a fake nose. He also was very good at convincing people to give him money, even royalty. Eventually, he worked his way up where the King of Denmark gave him an island and all its inhabitants, about 800 of them, and a bunch of money to build an observatory. Now, you might wonder, wow, how big a telescope did he have? He didn't have a telescope. Why would the man who has everything astronomical not have a telescope? Because nobody has one. There were no telescopes. So they were invented, after he died. That's another story. Yeah. In any case, what did Tycho do? The thing is, Tycho had a personality trait that was relevant here. He was, I can't retro-diagnose him, but it seems he's rather obsessive-compulsive, perhaps. At least he had an incredible attention to detail. Whether it was pathological or not, I don't know. But he would make observations of the positions of things in the sky with these giant protractors, like protractors that were bigger than this room with, very fine engraved degrees on them, tenths or hundredths or 60ths of a degree or whatever on them. And he would make meticulous observations, hundreds of them, to chart the motions of all the planets and everything. And he kept writing them all in a big book. Now, he did have a theory. I'm going to tell about his theory kind of quickly so you're familiar with it, but it didn't go anywhere. Listen to this clever idea. Tycho said he thought that the Earth was in the center of the universe. He had to believe the Earth was in the center of the universe, partly because he made these incredibly precise observations, 10 times the precision and detail of any ever before him, and he still didn't see stellar parallax. And that moved the stars even further away if the Earth was going to be moving, so the universe would be truly vast, and nobody wanted that. So no, he wasn't going to believe that the Earth moved. He did not believe Copernicus. However, he didn't mind if other things went around the sun. So here's what he did. He had the sun go around the Earth, and while the sun was going around the Earth, Mercury and Venus and Mars and Jupiter and Saturn were busy going around the sun. It's almost as if the sun became the center of all their epicycles. I kind of like that. I like that in the following way. One student asked a question earlier, like, what's in the middle of the epicycle? What's the planet going around? Ptolemy didn't know and he didn't care. It was just a mathematical point because nobody was thinking about forces causing these things to happen. As long as things were made of circles, you didn't really care if there wasn't a reason to orbit something. It was enough to say it was a circle. Tycho actually has things orbit the sun as the sun orbits the Earth. It actually works quite well in a way and stays geocentric. So I think if I lived at the time, I probably would have thought it was a pretty clever compromise, though it would definitely be a compromise. You know what, though? Not too many people believe that one. I think a few did. So we're going to forget about that now and talk instead about his observations. He made incredibly precise observations of Mars. And he tried to model Mars' position using his own model. And he couldn't get it right. It was always off a little bit. The amount by which it was off was something that would have never bothered anyone before Tycho, because no one before Tycho would have ever even noticed it. Mars would always be within where he predicted within 8 minutes of arc. And a minute of arc is a 60th of a degree. You can barely see this kind of an error, much less be bothered by it. But Tycho was bothered by it because his observations were good to 2 minutes of arc. So he's outside his error range. And he knew his model wasn't working. And he was frustrated. Then he did probably the most important thing ever. He got help. He hired a guy named Johannes Kepler, a German guy. Gosh, I could tell stories about both these people. Kepler was known for mathematical skills. He solved some famous problem about how much wine you have in a barrel when you put the dipstick in at different angles or something. I guess he got notoriety for that. But in any case, Kepler was a closet Copernican. Kepler actually believed Copernicus. Probably shouldn't talk about it a whole lot, don't want to get out. But Tycho hired him. I don't know if he knew Kepler believed that or not. But while Kepler's working for Tycho, trying to figure out what the heck is wrong with Mars, solve the mathematical problem there, Kepler probably has to keep his mouth shut about believing that the Earth moves because he's supposed to use his boss's. That's where his paycheck's coming from. He's supposed to use his boss's theory. So for a couple of years or so, he worked for him, and it was so frustrating. He couldn't resolve this discrepancy. No matter what he did with Tycho's system, even Copernicus' system or Ptolemy's, none of the systems could account for these little discrepancies in where Mars was in the sky. So Kepler was probably kind of wishing that Tycho wasn't in the way. He got all this great data, but he keeps telling him to use his model. Kepler wants to go do his own thing with it. He got his wish. I don't think he had anything to do with it. Let me tell you what happened to Tycho. See, Tycho was again, he just went to parties with noble people and asked them for money, and they gave it to him. I guess he was just fun at parties or something. In fact, actually, he had a psychic dwarf. I'm not making this up. His name was Jeff, and he would prophesy at Tycho's parties. Tycho's parties were even attended by such people as King James, as in the King James Bible of Scotland, or wherever England, wherever he's from. King James would go to like Tycho's parties. All these people kind of knew each other, I guess. Anyway, Tycho one night went to a party to try to get some money at the end of the party, hoping to leave with a check. The host is telling jokes, telling stories, and Tycho's sitting there listening and drinking big things of ale and eating big turkey legs or whatever. And Tycho really, really needed to excuse himself. But he was, for natural needs. But he didn't for fear of losing the check. And he held it. And I don't know if he ever got the check or not. But when he got home, he couldn't go to the bathroom. And he died a few days later of a horrid urinary infection. I don't know if his bladder literally burst or if that's possible, but it was bad and he died. And Kepler is left. Kepler somehow ran off with Tycho's data book. There are conspiracy theories that Kepler poisoned him or something, but no, it was probably just holding it at the party. In any case, Kepler now runs off with Tycho's data, gets far away to a safe place. There were actually legal issues about it. Tycho's family. He did actually get married and have kids. That is Tycho. There's so many stories about Tycho. But anyway, Kepler gets the data, and now he thinks he's going to get it all figured out. And he thinks maybe if he just doesn't use epicycles, he's got this idea, or he can use equants, but not epicycles, little technical details. He thinks he's going to get it all figured out. And he's so frustrated. He goes on and on and on. A year and a half, 70 different tries, and Kepler can't get Mars to be in the right place. Nothing is working. So finally, he decides to kind of go back to the drawing board. Remember we talked about assumptions? We talked about how Ptolemy assumed that the Earth's in the center and motionless, and all heavenly motions are perfectly circular and uniform. You try to work from there. Copernicus, in a way, not so different. Copernicus switches the Earth and the Sun, has the Sun in the middle and Earth going around it. He still used perfectly uniform circles. Tycho, with his system, even though it's kind of switched around where the other planets go around the Sun while that goes around the Earth, you think that's different? It wasn't that different. It made basically the same predictions for Mars, and they were just as wrong. Something deep down was wrong all along with everybody's system. Kepler decides to back off on his assumptions. He assumes just two things. Kepler assumes, first of all, that the Sun is motionless in the center. In other words, he is heliocentric. Remember, if the Earth is in the center, that's geocentric. So he believes in a heliocentric system. But watch this next assumption. He quits assuming that the motions are circular, and he quits assuming that they're uniform. He makes no assumption about what it is they actually, no particular shape he's going to assume. But here's what he says. He says orbits, whatever shape they are, and he doesn't even know, doesn't even pretend he knows. Orbits repeat exactly. He's just saying whatever it does it over and over again with a fixed period. He does not claim that they travel at a constant speed. He's just saying they'll be back again after the same amount of time. So in other words, it might do some crazy weird shaped orbit. He doesn't know. He doesn't even assume. He has no pretense of knowing what shape it is. But that they would come back to the same place after the same amount of time. Does he know this? No, he doesn't know this. He assumes it because you've got to assume something or you'll never get anything done. Generally, I use the example that when you go to school in the morning, you assume that Woodward is there and open. That assumption would just be an assumption today, wouldn't it? Well, the there part, it's there. I can go check. It's a mile from me. It's not open. This is our Woodward right now. Anyway, he makes these assumptions. And then he goes through a process that I'm going to briefly describe. I have not decided just how detailed understanding I'm going to expect of you, but please watch. This is Kepler's clever thinking. It goes like this. So he wants to find the orbit of Mars. Everybody's obsessed with Mars at this point because Mars is the one misbehaving. The other planets pretty much were where they expected to be. Mars was a renegade and was doing something different for some reason. So he knows that you can't tell where Mars is based on observations made by Tycho on the Earth unless you know where the Earth is. So before you can find Mars orbit, job one is going to be find the Earth's orbit, get the shape of the Earth's orbit. So here's what he does. He assumes the sun's in the middle, and he regards it as a fixed point. That's one of his assumptions. And let's just say, for example, he looks at the sun, makes an observation of the sun, and the sun, oh wait, I'll say it this way. Works better when I have a classroom with people in it. You can't totally find your way around by looking at one landmark with absolutely nothing else there. For instance, if you're in the middle of a dark lake in the middle of nowhere and there was just one lighted buoy out in the lake, you can't map your position by noting where you see that one light. You don't know how far you are from that light, maybe. Maybe you don't know how big it is and how to judge. Now, by the way, you have a background of distant lights along the shore of the lake, towns far miles away, that are like the stars. They're a metaphor for the stars. You can see that you're going around the buoy, the lit buoy, because you see the lit buoy travel against the background of those stars, the little street lights of faraway towns. But you don't know exactly what your path is unless you have two landmarks. If you had two landmarks like another buoy over here, two fixed points, then you can do this thing called triangulating. And it's how you find your way around the room. Every time you walk around anywhere in real life, you're looking at landmarks. Actually, you have thousands of them you can look at, but you could get by with just two if you knew where those two were. Here's why you could get by with just two. Because you might, for example, see the sun out here and see the sun, one of the landmarks, a person. When I do this in class, I usually pick two students and walk around like now I know where I am because I see this student over here and that student over there. Where must I be? I must be, gotta be there. I just found myself. And I can navigate that way. I can figure out where I'm going, whether I'm in control of it or not. For instance, if another time I saw this over here and this over here, I'd figure out I must be here. You see, I'm starting to find points on my path. So here's what Kepler did. He assumed the sun was a fixed point anyway. And then in addition to that, he needed another fixed point. He chose Mars. Now that's messed up because Mars is very definitely not fixed. It's moving. But you remember one of his assumptions? That the paths repeat with a fixed period? He assumes that whatever it is Mars is doing, whatever crazy stuff Mars does, it does it over and over again and could reliably be back in the same place at the same time. He has to find its period. Finding the period of a thing that's going around the sun when you also are going around the sun is a little bit difficult. I'll tell you what it's like. It's like if you're running around the track and someone else is running around the track maybe slower than you. Yeah, slower than you for sure. Someone else is running around the track slower than you, and you get curious about how long it takes them to go around. If you know you're running around the track every 2 minutes, let's say, and you're passing them once every, say, 6 minutes, then you realize if you lap them, you've just run one more lap than they did in the same time period. So let's think for a second. Normally I make the students think, but here's a video. So if I lap them once every 6 minutes, that means I've run 3 laps. But if I lap them, then that means they ran 2. If I ran 3 laps in 6 minutes, they ran 2 laps in 6 minutes. And being sneaky, I know they take 3 minutes. Right. Because I pass once every 6. It's right. So you do the same thing with Mars, and you find out that, how do we know we're lapping Mars? It retrogrades. We see Mars go backwards when we pass it. I hope you get that. So anyway, it's 687 days for Mars to come back to the same place. So by making an observation once only every 687 days, Kepler can plot Earth's orbit. But that would take so long. You need like 20 or 30 points. 687 days is almost 2 years. That's a lifetime. Guess whose lifetime? Tycho's lifetime. Kepler didn't have to go out and look. Kepler had to book. Kepler just flipped some pages, counted on the calendar, 687 days from October 13th, 1587 or whatever, counts the days and looks to see where it was in Tycho's data. So Tycho did all the dirty work, going out in the cold, making the observations. And so Kepler is able to plot Earth's orbit. He finds out that the Earth travels in what seems to be a circle. As far as he can tell, it's a circle. Can't tell it's not. But he noticed the sun was a little off center. I'm going to exaggerate that on this other picture so I can make my point here. So he finds it's a circular orbit pretty much with the sun off center. And then he finds out something interesting. He sees that you're going faster when you're closer and slower when you're further away. Kind of like Ptolemy did, that made Ptolemy come up with the equant thing. Only Ptolemy had the Earth in the center and the sun going around. This is the sun in the center and the Earth going around. But either way, it goes faster over here and slower over here. Now, whereas Ptolemy came up with this weird equant happy place thing, Kepler looks at it differently. Kepler says, oh, look, if these were pieces of pie, these are same time intervals, like a month. Say, pick a month or something. And the Earth goes this far in a month here, goes this far in a month here. And actually, this is January, maybe, and this is July. That's actually about right. He found that, like, if this distance were shorter than this distance, then this thing would be proportionally wider. So the areas of these two triangle-y things were the same. He comes up with something called the law of areas. And it's printed in your PDF thing. I'm not going to write it up here right now. The law of areas, that the line from a moving planet to the sun sweeps out equal areas and equal time intervals. What a weird thing to come up with. But that's what he realized. So he found that for the Earth. But now, what was he really after? Mars orbit. So he needs to find Mars orbit. So how does he do that? Well, he's already got Earth's orbit now. And he's got all these points on Earth's orbit. He knows when Earth is everywhere. And then you flip this method around. For example, he sees that on a certain date, I don't even know what date, something in 1587 or something, Mars appeared to be out there. 687 days is just under 2 years. So just under 2 years later, Earth is, I don't know, here, let's say. And then he looks to see where Tycho saw Mars, and it appeared to be out there. And that means if Mars was really in the same place, because this is a 687-day difference in these dates where the Earth is not in the same place, it must have been there. And by the way, this is what you do with your eyeballs. Look, watch my eyes. I'm going to watch this marker. So you have to cross my eyes to look at it. When you cross your eyes, your brain knows you're looking at, knows the distance. It's depth perception. It's triangulation with the angle between your eyes. Telling you, I could use 2 markers. Okay. Anyway, so he gets these points on Mars' orbit, and he plots its orbit. And its orbit is also off-center. It also obeys the law of areas. It's not just the Earth. Apparently, a line drawn from Mars to the sun sweeps out equal areas and equal time intervals. So he's kind of generalized it like planets in general do this now. Obey this law of areas. That's one law. But then he looks very closely, and he had to look really, really closely and do a lot of analysis. He finally finds that Mars' orbit is not a circle. Remember, he quit assuming that it was a circle, and everybody else had always assumed that orbits were all circles, and he doesn't assume it's a circle. He figures out it's an ellipse. An ellipse is the shape you've heard of, and here's how you can make an ellipse. I'm not going to do it right here, right now, with a thumbtack like I'm talking about, but if you took a thumbtack, you took another thumbtack, you took a piece of string and stretched out the piece of string, wrapped it around the thumbtacks, and got your pencil here, took your pencil, stretched it out tight, and then keep the string tight, drag the pencil around. The pencil will make one of these things. It's called an ellipse, and these are called the foci. Each one is a focus, plural foci. Now, I think you can tell that really, hey, fill this in. Circle is to square. Circle is, let me try again, I'm sorry. How about this? Square is to rectangle as blank is to ellipse. Circle. Circle is to ellipse. You see, a circle is like this special case of an ellipse where the foci are together, just like a square is a special case of a rectangle where the dimensions are the same. Anyway, so a circle is an ellipse. Circles aren't prohibited here, but it's just a more generic thing. Broaden your horizons here. You could have the foci apart from each other. So he finds out that Mars' orbit is an ellipse. And where's the sun? It's at one focus and not the other. In fact, the other this bothers me a little bit. It's empty. Nothing's there. It's almost as bad as it's about half as bad as an epicycle, a point where nothing lives. Okay. So, in any case, he finds that orbits are ellipses with the sun at one focus. That's his second law. Another thing he finds, I'm going to say it really fast so I can get all of Kepler's laws said, is he has data on the radii of the orbits of the planets, Mercury, Venus, Earth. He does it the same way. He does the same thing over and over again. Earth, Mars, Jupiter, Saturn. And I'm going to use a unit called the AU. The astronomical unit is the distance from the Earth to the sun. So guess what? Earth, 1 AU from the sun on average. It varies a little bit because it's an ellipse. But and this is the period in years. Guess how long the Earth takes to go around? 1 year. Mercury is like 0.39 AUs and takes 0.25 years. This is just data he figured out. Copernicus kind of had about the same numbers too. Venus is 0.72 AUs, and this is 0.62. Mars is 1.53 AUs because he maps it. He's got the picture. He drew the picture. And it takes 1.88 years. That's the 687 days. Jupiter 5.2 and 11.86, and Saturn is like something like 9.54 maybe, and 29.7, something like that. He spent 9 months trying to figure out what the heck is the pattern. Clearly, the further a planet is from the sun, the longer it takes to go around, but it's not direct proportion. Look at this. Like Jupiter is over 5 times as far from the sun, just over 5 times as far from the sun as the Earth is. It takes almost 12 times as long to go around. It takes longer partly because it's got further to go, a bigger trip to make, but also because it goes slower. But how much slower? This much slower, whatever, a bunch of weird numbers. He didn't know, nobody told him how to find this relationship. You actually know. You learned it the first week of school. You would make a graph of T versus R, and it would have a shape. And you know what you would do. I'm going kind of fast here, but just to jog your memory here. Yeah, it's power law. Mother Nature's favorite. First week of school, told you to be back. In any case, I'm not going to make you go through the process again. We've got to move on here. But it turns out it was more than a first power law. Too curved to be a first power law, but it wasn't really the second. Guess what? It was the 1.5, the 3/2 power law. And so Kepler took 9 months to figure this out. Nobody told him to graph it. Nobody told him about power laws. Nobody even told him to use that kind of math called algebra. So he finally figured it out. The squares of the periods are proportional to the cubes of their average distances from the sun. The proportionality constant means, that fishy sign means equals a constant times. So it's equals a constant times. However, you're in luck. It is your lucky day. Look at this. As long as we use AUs and years, we can plug in a 1 and a 1 for one of our points. And a 1 there and a 1 there makes a 1 there. Guess what? K is 1. Now, I'm going to shut up now and post something in a little bit for you to do with this. You got that nice handout to use, but we have just learned Kepler's laws of planetary motion. Let me point out one more thing. He had no clue why these things should be true. What in the heck? 3 weirdly different laws look like they're pulled out of a hat. Got to be some connection. He has no idea what it is. That's where the story gets really good. Anyway, I'll shut up now and talk to you later. Bye.